Welcome to another episode of Terry's Notes, and today we are going to be looking at rates of reactions. Now, first thing we need to be able to do is to explain what is meant by the term rate of reaction. Now, the rate of reaction is a change in concentration of a reactant or product with time at a stated temperature. Now, many students get confused with its definition. The rate of a reaction is not the time taken for a reaction to take place. It is simply the change in concentration of a reactant or product with time at a stated temperature. So, during the course of a reaction, the concentration of the reactants decreases. So, we have this representing a decrease in concentration over time. And in a reaction, the concentration of the products will also increase. So we have this happening here. Now, essentially what the rate of reaction is saying is that let's look at the product curve. The concentration of the product is increasing. So if we wanted to say what the rate of the reaction is at this point here, essentially what we have to do is to draw a tangent to this curve at this point and determine the change in concentration over time. So what we're saying is that rate is equal to your change in, now in chemistry we write concentration in square brackets. So we write products. So delta is change. So change in products over the change in time. So this is how we define rate. So make sure you are clear as to what the definition is. It is the change in concentration of the products with time at a stated temperature. And the reason why we say at a stated temperature is that temperature affects the rate of a reaction. Okay. Now we also need to know the factors that affect the rate of reaction. And there are several factors that affect the rate. The first one is concentration of the reactants. Second one we have is pressure, and this usually applies to gases. Particle size or surface area affects the rate of a reaction. I said earlier that temperature also affects the rate of a reaction, and the presence of a catalyst also affects the rate of a reaction. So you need to know what are the different factors that affect the rate of a reaction. Let us look at concentration. Okay, so the increase in the concentration of the reactants increases the rate of a reaction. Alright, so we need to know that and why. When we increase the concentration of the reactants, we increase the number of particles per unit volume present in the reaction mixture. What this means is that the collision frequency, or the frequency of collisions between the reactants increases. Now, for a reaction to take place, the reactants must come into contact with each other. They must collide, and they must collide a certain way. So what we are saying is that once we increase the concentration of the reactants, the rate of the reaction will increase. And why? We increase the number of particles per unit volume, and this therefore increases the frequency of the collision between the reactants, and hence the rate increases. Now you have to be able to describe a simple experiment to measure the rate of reaction. In this case we have calcium carbonate plus hydrochloric acid producing calcium chloride, water, and carbon dioxide. We can measure the rate of this reaction by measuring the volume of carbon dioxide being produced over a period of time. So we have a conical flask with the calcium carbonate and the hydrochloric acid, and we are collecting the gas in a syringe so we can measure the volume of the gas. And something that's not drawn here is we need to have a stop clock. because what we are doing is we are measuring the volume of carbon dioxide produced over time. Now, when we collect that data, we plot a graph of volume of carbon dioxide produced against time. And the carbon dioxide is one of the products in the reaction. Therefore, the volume of carbon dioxide will be increasing. So this represents the general shape of that type of curve for this particular experiment. And we need to be able to explain certain things on this curve. Now, the rate of reaction is simply the gradient of the curve at a point. So at time t equals 0, let's say at this point here, this represents, if we draw a tangent at this point here, we're going to get a tangent that's going to look something like this. And if you notice, that line is very steep. So at time t equals 0, the reaction is fastest at this point. Why? At time t equals 0, this is when the reactants are mixed. So the concentration of the reactants are at their highest value. Therefore, we have a high concentration of particles per unit volume, and therefore the rate of reaction is going to be the fastest at t equals 0. Let's look at this point P here. At the point P, we have used up some of the reactants. Therefore, the concentration of the reactants have decreased a bit. And if we draw a tangent at this point here, at the point P, we notice that now the gradient of this tangent, this line is less steep than the one at t equals 0. So therefore, just by looking at it, we know that the rate of reaction has decreased. And we are saying that this decrease occurs because the concentration of the reactants have decreased. And then at the point Q now, we notice that the graph has flattened out and the gradient is now 0. When the gradient is 0, this means that the reaction has stopped. And what this means also is that all the reactants, or most of the reactants, have been used up, right? You need to understand the concept of limiting reagent. So the limiting reagent, we say, have been used up. Now, we need to be able to show graphically what happens when we change concentration. So we have, in this slide, we have 3 experiments. In each experiment, we have the same mass of calcium carbonate. We have 1 gram of calcium carbonate. But what we are doing is changing the concentration of the acid. We are increasing the concentration of the acid. So we have 0.5 mole per dm cube in experiment 1, 1 mole per dm cube in experiment 2, and 2 mole per dm cube in experiment 3. And we have the same experimental setup as previously, and we need to look at and see what happens to the curves. So in experiment 3, we have the highest concentration of the acid, and this is represented by this curve here, and this is the curve for 1 mole per dm cube, and this is the curve for 0.5 mole per dm cube. So what we notice is that when we increase the concentration of the acid, we increase the rate of reaction. Notice the difference between the 3 curves. At time t equals 0, the curve representing 2 mole per dm cube has the highest slope. That is this one here. Then if we decrease the concentration, that's the 1 mole per dm cube, the slope is less again. And when we look at this one, the 0.5 is even less steep. Right? So you need to be able to represent the changes graphically as we change concentration. Another way we can measure the rate of reaction is by looking at the decrease in mass of the reactants. Now in this experiment, we have calcium carbonate reacting with hydrochloric acid. We are producing calcium chloride, water, and carbon dioxide. So over time, the mass of the calcium carbonate will decrease. So what we do, we have the reaction mixture on an electronic balance, right? and we measure the mass of the mixture over a period of time. So obviously we know the mass will decrease, so the curve will basically look like this, and it will decrease over time. To measure the rate at, let's say, this point here on the curve, we simply draw a tangent and find the gradient of the tangent. Now the effect of particle size. When we decrease the particle size of the solid reactants, we increase the rate of a reaction. So what we are saying is that if we have, let's say, calcium carbonate, we have marble chips and we have marble powder. The reaction is going to be faster with marble powder than marble chips. Why? You need to know the explanation as to why. In a reaction with where solid reactants are involved, the reaction occurs on the surface of the solid. Breaking the solid reactants into smaller pieces increases the surface area. So the key thing here is that when you break it up, you are increasing the surface area. Since more surface area is exposed, we have more collisions taking place, and therefore the reaction rate increases. So let's look at it graphically again. We have two experiments here. We have, in the first one, we have 1 gram of calcium carbonate and 1 mole per dm cube hydrochloric acid. But in this case, we are using marble chips. And in experiment 2, we have 1 mole per dm cube of the hydrochloric acid and 1 gram of marble powder. So we know that in experiment 2, we have an increased surface area, and we expect in experiment 2 for the reaction rate to be greater. And this is shown graphically here. So graph 1, that is this one, represents the marble powder, and graph 2, this one, represents the marble chips. Notice that the both graphs end up at the same level when the reaction is complete, and the reason for that is that we are adding the same amount of calcium carbonate in both experiments, and we are using the same concentration of the hydrochloric acid. The effect of temperature. Now we know that increasing the temperature of a reaction mixture increases the rate of a reaction. Right? Now, what is the explanation for this? Increasing the temperature increases the kinetic energy of the particles. They move faster and collide more frequently. And more particles have energies greater than the activation energy. The energy is sufficient to break more bonds in the reactants. So, once we supply energy to the reactants, they begin to move more rapidly. So we therefore increase in the kinetic energy of the particles. If they are moving faster, they will collide more frequently. And remember, in a reaction, we have what is called the activation energy, which is the minimum energy required for reaction to start. And therefore, we're going to have more particles having an energy greater than the activation energy. And therefore, we have enough energy to break the bonds in the reactants. So therefore, the rate of reaction increases. So again, we need to illustrate this graphically. So we have two experiments in this case. We have magnesium reacting with hydrochloric acid. We have 1 gram reacting with 1 mole per dm cube hydrochloric acid, and the temperature of this is at 25 degrees. And in the second experiment, we have 1 gram of magnesium and 1 mole per dm cube of hydrochloric acid, and the temperature in this case is 80 degrees Celsius. Now, graphically, we have the two experiments. So experiment 1 is at 21 degrees. So this graph here represents the experiment 1 at 25, and this graph represents experiment 2 at 80 degrees. So we notice that in experiment 2, the curve is steeper at time t equals 0, So therefore, in experiment 2, the reaction rate is faster. The effect of a catalyst. Now, a catalyst usually speeds up the rate of reaction. Why does it do this? Adding a catalyst changes the rate of a reaction, but is chemically unchanged. The catalyst provides an alternative pathway with a lower activation energy. So the key point here is that it reduces the activation energy by providing an alternative pathway for the reaction to take place. So for example, hydrogen peroxide, which is H2O2, decomposes slowly to produce oxygen gas. But if we add manganese dioxide, which is MnO2, the reaction speeds up. So we have 2H2O2 produces 2H2O plus O2. Another example of a process where a catalyst is used is in the Haber process. We use iron, and the Haber process is the process by which we produce ammonia gas.